everyone, and welcome back to this series on the foundations of mathematics. Today we're going to be continuing our exploration of quadratic relations and look at a couple applications and another method in order to find equations of quadratic relations in this little discussion that we have going on. So let's jump right into it. So the first thing I want to do is introduce a very common application that is associated to basic fundamental physics, and that's gravity, free fall, and projectile motion. So let's assume that we have x representing position and then h of x representing height at each of these positions. Let's assume that we have a position here, so we can, for example, call this h0, corresponding to the initial height, and let's assume that we project some object from this particular point, and then this is going to eventually fall. So under some certain physical conditions, the path that this projectile will make will follow a parabolic path. So what do we have exactly going on here? So we have an object, and it's going to be projected at this particular elevation, at that particular angle, and then it's going to fall eventually, and then eventually hit the ground at some point later in the future. Right? So let's assume that this actually does follow a parabolic path, and let's assume that this parabolic path is characterized by the quadratic relation h of x is equal to negative 0.0327 x squared plus 1.12x plus 7.32. So the shape or the rate of change of decrease and how far and the angle, because technically speaking, if you change this angle theta for which you project this object, it's going to reach a different maximal height. It probably will go farther depending on gravity, maybe a little wind resistance will change these coefficients, but this and this coefficient right here is going to be characterizing that path, and this number here, if you notice, if I do, for example, h of 0, we get this 7.32 value hanging out on the end. So what exactly does this 7.32 quantity correspond to? Well, that's obviously going to be the initial height. That's the initial height. So this h0, for example, is going to be equal to 7.32. And let's assume that this unit is in feet. Right? So what else do we know about this particular object? So if we look at this particular quadratic relation and look at its leading coefficient, what can we say from that? So since the leading coefficient of this quadratic relation is less than 0, then what can we tell about the overall structure of this parabola? Then the parabola, or the parabolic relation, has a global maximum at its vertex. Right? So that's one of the important properties associated to quadratic relations. That is, if the leading coefficient is negative, then its vertex, which is going to be located somewhere around here, right? So there's this point here called x subscript v, the x-coordinate of its vertex, for which is going to attain its maximum height. So its maximum height is going to be this distance right here. So that's h max. Right? So let's see if we can find out where exactly that x value is for which it does attain its maximum height, and then we can figure out what its maximum height actually is. Right? So building upon this very important quadratic theorem, let's just recall a basic fact. So if we have a quadratic relation y is equal to ax squared plus bx plus c with a not equal to 0, then the x-coordinate of the vertex will be equal to negative b divided by 2a, which you can easily verify by using the symmetry of the x-intercepts, and it's always going to be the average of those two numbers. So, based upon our particular quadratic relation, what will that give us? So that means the x-coordinate of our vertex is going to be equal to negative b, which came out to 1.12, all over 2 times a, which is negative 0.0327, which once you actually do out that calculation, that's going to be approximately 17.13 feet, right? So that's how far this object travels until it reaches its maximum height. So now that we know the position, now we can use that quadratic relation to figure out what that maximum height actually is. So therefore, h max is going to be equal to the height evaluated at the x-coordinate of our vertex, which is going to be approximately equal to h evaluated at 17.13, our x-coordinate of our vertex. So once we plug this 17.13 into our quadratic relation, what is that going to give us? So let's just write this out. So that's going to be negative 0.0327 times 17.13, the quantity squared, and then plus 1.12 times 17.13, and then plus our initial height of 7.32. And once you work out that calculation, that's going to come out to approximately 16.91 feet. So it starts off at an initial height of 7.32, and then it increases approximately 9 or so feet into the air more, and then eventually once it reaches the 16.91 feet, then it's eventually going to drop down and eventually hit the ground, and eventually will stop moving once its h value is equal to approximately equal to 0. Okay, so now that we know the point for which it attains its maximum height, and also that maximum height, now let us figure out when it actually hits the ground. So let's formally state this question. So when does this object land? Right? So this object is going to land, obviously, when the height is equal to 0. So let's again recall a very important property, because when the height is equal to 0, that's going to give us the x-intercepts of our function h. So recall that when our quadratic relation is given by y is equal to ax squared plus bx plus c, with a not being equal to 0, then y is going to be equal to 0 when x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's our famous little quadratic equation. And again, in case you don't remember, this object here, b squared minus 4ac, is sometimes represented by delta and represents the discriminant of our quadratic relation. Right? So let's take another look at the graphical representation of our projectile motion problem. So keep in mind the initial height is somewhere up there, and then it's eventually going to fall. But technically speaking, the height does not exist on the left because it's going to be projected from that point forward, and technically the height's not going to exist after it's going to hit the ground as well. So if we want to be a little bit more precise, then this is going to be a solid curve, and then it's going to be dotted line from there. Right, so obviously the domain of this particular relation h is going to be equal to 0 to some x landing, let's say it is. That's when the object is going to land. So that's going to be this particular point right there. Okay, so how are we going to find the x-intercepts? So the theoretical x-intercept, if the domain was chosen to be all real numbers, is going to be located here and located here. So this point is going to be x is equal to negative b minus the square root of the discriminant all over to 2a. And this point right here is going to be x is equal to negative b plus the square root of the discriminant all over 2a. So this is going to be the value or the position for which our object is going to land. So therefore what? So therefore this value is not going to be of interest to us. Therefore that one's the only one that we really care about. So h is going to be equal to 0 when x is going to be equal to negative b. So negative 1.12 plus or minus the square root of b squared, 1.12 squared, minus 4 times negative 0.0327 times 7.32, all under the square root, all divided by 2 times the leading coefficient, negative 0.0327. So once you actually work out all that fancy and fun math, we're going to have that our x landing position is going to be approximately equal to 39.87 feet. So that's going to be the horizontal displacement of our particular object. So now that we have all these numbers, it's probably going to be very useful to sort of draw a nice little picture with all of our numbers inside of this diagram. So again, we have x here, we have h of x here, and then we have our projectile going down here. So what do we have here? So this is going to be our initial height. That's going to be 7.32. And we also figured out what the maximum height is going to be. So this maximum height. So this distance right here, that's going to be equal to 16.91 feet. This point for which it attains its maximum height is approximately equal to 17.13 feet, and it eventually hits the ground somewhere over here at approximately, let's make the diagram more formal, and that's going to be 39.87 feet. Right? So that's a nice little diagram that sort of sums up our little projectile motion problem. So that's one application that you can use for quadratic relations. So let's consider this other engineering problem. Suppose you have 512 feet of fencing and you want to make a rectangular pasture for your farm animals. What is the maximum area that you can generate from this amount of fencing? So let's just draw a picture to sort of get a feel for what's actually going to be going on here. So what we're going to have is we're going to have our rectangular pasture. Right, so this is going to be our rectangular pasture. So that means these corners are going to be 90-degree angles. And we need to figure out what the dimensions of this rectangle are going to be for the area of this rectangle to be as high as possible or as large as possible. So this is going to be x, let's say. Let's call this x. Let's call this y. Let's call this y. Now you could call the vertical ones y and the horizontal ones x. It doesn't really matter. You'll get the same exact answer. But from this particular definition, what we're going to have is we're going to have that 2x plus 2y, the perimeter, so the perimeter is going to be equal to 512 feet. Right? So obviously we can clearly see that we have 2, 2, and a number that's also divisible by 2 in this particular equation. So we can actually divide everything by 2 just to make this equation just a little bit more nicer to deal with. This is going to give us x plus y is going to be equal to 256. Now what we have here is we have a function that has two different variables in it, x and y. So it's going to be really, really hard to solve this problem unless we make a function that only has one variable, unless you know a little bit of multivariable analysis. So what we can do is we can solve this equation for one of the variables, for example, y, and then we're going to have that y will be equal to 256 minus x. Now, is it possible that you can solve that equation for x also and get another relation? Sure, but how you use that particular information is going to change in the next step. So what is our goal? So our goal is to maximize area. So if you have an area with dimensions x and y for its height and width, or height or length, whatever, then the area is going to be equal to x times y. Now, we want our area to be a function of one variable, so let's assume that we want to represent a as a function of x. That means we need to write y in terms of x, and we already have a relation that does so. Of course, you can write a as a function of y. That is perfectly okay. You will still get the same exact answer, but I'm just going to use x in this case. So therefore, when we write a as a function of x, that's going to be equal to x times y, but y is just going to be equal to 256 minus x. So now we have a function of x, and also notice it's a product of two polynomials of degree 1, which is going to give us a degree 2 polynomial, and as we can clearly see, this will be a quadratic relation. In particular, once we actually distribute that out, what are we going to have? We're going to have 256x minus x squared. So we can clearly see here that for this quadratic relation, our leading coefficient here is going to be equal to -1, which is negative. And what do we know about quadratic relations that have negative leading coefficients? Well, that means that the parabola is going to be facing upside down, which means its vertex is going to give us a global maximum for that relation, and that is going to give us what? A maximum area. Right? So this particular point here, x, is going to give us one of the dimensions that we need. Once we have x, we can find y, and then we can find the maximum area that can be generated from this presented amount of fencing. Right? So that's great. That's wonderful. So let's actually sketch this out in a more neater fashion. So what do we have? So we have a of x is equal to, once we rearrange this, -x squared plus 256x. So our goal is to figure out what is the value that can maximize this particular area function. Now, from the factored form, the factor form is not completely useless to us. We have x times 256 minus x. So we have two zeros. We have x is equal to 0 and x is equal to 256. So the zeros of this function are actually very easy to get from this maximum function. So what do we have here? We have an x-intercept here and an x-intercept here of 256 and 0 respectively. So where will be the x-coordinate of the vertex? Well, it's going to be the mirror image of 0 and 256, but you can technically use our relation from before, negative b divided by 2a, and that's just going to be equal to negative 256 all over 2 times negative 1, and that's just going to be half of 256, which is going to be equal to 128. So that's going to be the value of our vertex, right, which is going to be equal to 128. And that's going to give us the value that's going to generate the maximum area, right? So that's wonderful. So that means what? So that means if x is going to be equal to 128, that means y is going to be equal to 256 minus that x value, 128. And keep in mind, this is not just any x, but this is going to be the x and y that are going to generate the maximum area. That's also going to be 128. So what do we know about a rectangle whose x and y values are equal to each other? That is going to be a square. Isn't that beautiful? So that means that in order to maximize the area of a rectangle, you need to have a square, right? At least under these geometry assumptions. So what does that mean? So that means once we have our dimensions 128 and 128 feet respectively, that means the maximum area is going to be equal to what? Well, it's going to be the area function evaluated at the x-coordinate for the maximum, which is going to be equal to 128 times 256 minus 128, or 128 in disguise, which is just going to be equal to 128 squared, which is going to be equal to, I think, 16,384 square feet, right? So that is the maximum area that you can generate from 512 feet of fencing, which of course is going to be generated to a square. The next problem I want to discuss in terms of quadratic relations isn't really an application per se, but it can be used to generate quadratic models for either 3 or possibly more points if you're up to approximation theory. So before we get into the quadratic relation part, let's just review a couple important things from linear relations that can sort of motivate you to sort of get this solution. So let's assume we have these 2 points, x1, y1, and x2, y2. And I ask you, how many curves pass through these points? Well, actually, there's infinitely many curves that pass through these points. For example, you can do a parabola through these 2 points. You can do a line through those 2 points. You can do some fancy curve through those 2 points. There's infinitely many curves that pass through those points. But if I ask you how many lines pass through these 2 points, you should be convinced to some degree that there's actually only one. In particular, there exist these numbers a and b, such that y is equal to ax plus b, such that when you plug in x1, you get y1, and when you plug in x2, you get y2. So what we have here is a unique, that's a weird looking cue, so a unique linear relation through these 2 points, right? And how would you find these numbers? Well, obviously a will be equal to y2 minus y1 over x2 minus x1, and then b can be found a variety of different ways, but probably one way you could do is y1 minus x1 times that a value that you just found, and that's going to give you your b. And you could also use x2 and y2 to get your b. It doesn't really matter. You only have one solution for that. Now, how is this going to sort of tie into the discussion of quadratic relations? So obviously, if I give you 2 points, there might be a couple parabolas that pass through them, but what we're going to be doing is looking at 3 points instead. And if I ask you how many parabolas pass through these 2 points, you should be convinced that the correct answer is 1. Right? So obviously we're going to be looking for numbers a, b, and c, such that ax squared plus bx plus c is going to pass through these 3 points. And our goal is to find this unique quadratic relation that passes through these 3 points. And it's very important also to keep in mind that both for the linear and the quadratic interpolation problem, these points cannot stack vertically, else it's not going to be a function anymore. Okay, so this is going to be what we're going to be given. So we're going to be given 1, 2, 3 points that do not have repeated x values, and our goal is to find what is this number a, b, and c that characterizes a quadratic relation that passes through all 3 points. Now, let's look at a numerical example to sort of guide us through this exploration. Let's assume we have the number or the point 1, 2, 2 minus 1, and 3 minus 8. And our goal is to find our quadratic function f of x, which is equal to ax squared plus bx plus c. That gives us these points and, of course, more. So what happens when I plug these 3 points into this relation? Let's start with the first. So that's going to give us a 1 squared plus b times 1 plus c, and that must generate a value of 2. Similarly, a 2 squared plus b times 2 plus c must generate a value of minus 1. And then finally, a 3 squared plus b times 3 plus c must generate a value of minus 8. Right? And obviously we can clean this up a bit, and this is just going to be equal to a plus b plus c is equal to 2. And then we're going to have 4a plus 2b plus c will be equal to minus 1. And then finally 9a plus 3b plus c will be equal to minus 8. So what exactly have we built here from these 3 points? So what we have here is just a system. It's a system of 3 linear equations with 3 unknowns. And those unknowns are a, b, and c that we're aiming for. Now, using a little bit of slightly, not really advanced math, but another course called linear algebra, one can prove that as long as these x values do not have repeated x values, the system is actually always going to have a unique solution, right? So we're always going to be able to find a unique parabola that passes through these 3 points, as long as it doesn't break that assumption of repeated x values, right? So how are we going to solve a system of 3 equations and 3 unknowns? So now we're going to use a method known as elimination. Now, obviously, I have some other videos in my linear algebra series that sort of go through sort of what's going on here with elimination, but I'll give you sort of a little sneak peek as to how elimination can be used to solve 3 by 3 or 4 by 4 or even 10 by 10 systems of linear equations with multiple unknowns. So our goal is to look at these coefficients 4, 9, and 1 and ask ourselves the following question. Is it possible that we can turn 4 into 0 by multiplying 1 by something, multiplying 4 by something, and then combining those 2 results with addition or multiplication in order for that 4 to turn into a 0? Yes. Let me sort of walk through what that question actually looks like in the mathematical realm. So if I multiply equation 1 by 4, that's going to be 4 times 1, which is going to be equal to 4, and I minus 1 times equation 2, because equation 2 is just 4, right? So 4 times 1 minus 1 times 4, that's what we have here, that's going to be equal to 0. So instead of that being equal to 0, I'm actually going to do it for all of my coefficients inside of my equation 1 and my equation 2. And what I'm going to do is I'm going to define this to be a new equation 2. Right? And similarly, I'm going to do the same for equation 3. I'm going to multiply 9 by equation 1. I'm going to subtract 1 times equation 3, and I'm going to define that to be my new equation 3. Okay, so that is going to be what I'm going to do, and let's sort of see how that comes out. And you might want to pause this video and try this on your own just to see if you can get it. Right? So what are we going to have? So we're obviously not redefining equation 1, so equation 1 will stay the same. So we're going to have a plus b plus c is equal to 2. And then we're going to do the same for our other equations. So let's take a look. So we're going to have a plus b plus c is equal to 2. And let's take a look at equation 2. So 4a plus 2b plus c is going to be equal to negative 1. So 4 times 1 minus 1 times 4, that's going to be equal to 0a, right? So we're not going to have any a's on the second equation. Now we're going to be doing 4 times 1 minus 1 times 2. So 4 minus 2, that's going to be equal to 2b. And then 4 times 1 minus 1 times 1, that's going to be equal to 3. And then finally 4 times 2 minus 1 times negative 1, right? So the negative negative becomes a positive, so we're going to have what? So 4 times 2 is 8 plus 1, that's going to be equal to 9. And then you're going to repeat that process for equation 3, and I don't need to write that plus sign there. But if you get the correct answer, you're going to have 6b plus 8c will be equal to 26. Okay, so now we have this systems of equations, and we can actually do a little bit of simplification on this last equation because everything is divisible by 2. So we can write this system as a plus b plus c is equal to 2. 2b plus 3c is equal to 9, and 3b plus 4c will be equal to 13. Now, what I want you to sort of focus on is just the last 2 rows. Notice that I only have b and c there, so that's actually a sub 2 by 2 system of linear equations, which you should be able to solve via, for example, elimination, or maybe isolation and substitution if you remember how to do that. But what I actually want to do is sort of continue this elimination process, and I'm going to do 3 times row 2 minus 2 times row 3, and that's going to give me a new row 3 for that particular system, right? Because notice 3 times 2 minus 2 times 3 will be 0, right? And then we're going to have some stuff for c in our coefficients on the right-hand side. So what is that going to give us? So we're going to have a plus b plus c will be equal to 2. We have 2b plus 3c is equal to 9 since we're not redefining our equation 2. And 3 times 2 minus 2 times 3 will be 0. And then 3 times 3 is 9 minus 2 times 4 is 8. That's going to be equal to 1. So we're just going to have 1c. Uh-oh, we're about to get our c value here. So what's c going to be? So we're going to have 3 times 9 minus 2 times 13. And you should find out that that's actually just coming out to just 1. Okay, so that's beautiful. So now we have our value for c. Now let's go back into equation 2 and figure out what b is. And then once we have b and c, we can go back into equation 1 and find out what a is. So what do we have? So we're going to have 2b plus 1 will be equal to 9. So 2b will be equal to 8, so b must be equal to 4, right? So that's going to be pretty wonderful. And then what are we going to have? So let's make sure we didn't do anything wrong. It seems I have forgotten my little 3. So let's put our little 3 back in there, right? Because we forgot about our lonely little 3. So 2b plus 3 times 1 will be equal to 9. There we go. So now we have 2b must be equal to 9 minus 3. That's going to be 6. So b will be equal to 3. That sounds a little bit better. And now let's go back to equation 1. All of our coefficients are 1. That's beautiful. So we have a plus b plus c will be equal to 2. So that's a plus 4 will be equal to 2. So that means a must be equal to minus 2. So now we have that particular coefficient. So now let's recollect and organize. So that means our quadratic relation, f of x, is actually going to be given to be minus 2x squared plus 3x plus 1, right? There's our a, there's our b, and there's our c. Right? Now, since there's so many different places that you can make a mistake on, you should be able to look at your points, 1, 2, 2 minus 1, 3 minus 8, and analyze to make sure these points satisfy. So when you plug in 1, you should get 2. When you plug in 2, you should get minus 1. And when you plug in 3, you should get minus 8. And once you have verified all 3, that means you have the right quadratic relation that models through those 3 points. Right? So those are just some of the basics that you definitely should know when you want to work with modeling quadratic relations, and some of the tools that you definitely should know when using quadratic models, such as finding x-intercepts, finding vertices, whether the parabola is facing up, facing down, via the leading coefficient, and so many other things. So I hope you enjoyed this video, and I'll see you in the next one. Take care.